welcome to Teacher Gimbal channel. Today we'll be going over Illustrative Math Geometry Unit 1, Lesson 15. If you like this video, please make sure to like and subscribe by hitting the button down there. And if you want more videos like this, or if you want custom videos, you can subscribe to my Patreon, which you can find in my description, and I'll make you custom videos on any topic that you need, whether it be illustrative math or something else. So go ahead, sign up there if you want your own videos custom made just for you. Let's get started. Problem 1. For each figure, identify any lines of symmetry the figure has. Now, lines of symmetry is a concept that you might recognize from earlier grades. And what it basically means is, can we fold the figure in half in any direction so that the figure lines up exactly on itself? So this circle, or this yin-yang, when I would fold it over this line, and here I use the phrase fold it because we like to imagine something folding onto itself, but what we're actually doing here is we're reflecting it over that line. So if I reflect this side of my figure onto that side, my black and white sides do not line up. So that is not a line of symmetry. I'm going to check what happens in that direction, and the black dot is going to go onto the white dot, but our figures are still not going to line up. So looking at the shape, I see no lines of symmetry. Here, I notice if I draw a line straight down the middle, if I reflect this triangle over, it's going to lie exactly on that triangle. This half will lie here, this half will lie there. So we do have a line of symmetry that goes straight down the middle. I also notice that if I draw a line of symmetry this way, the same thing happens. We reflect each part, and it's going to line up exactly with the parts on the opposite side. So this does have a line of symmetry because when you reflect it over that line, the one side maps exactly onto the other side. Now for our pinwheel with the legs, I don't think I see any way where I can fold it or reflect where the figures match up onto the other figures. So I'm going to say no lines of symmetry here. And we're done with this question. Pause the video if you want to take a second and look at these figures on your own and determine if you can find any other lines of symmetry. Problem 2. In quadrilateral BADC, AB is equal to AD. So this guy is the same length as this guy. BC is equal to DC. So this guy is the same as this guy. And line AC is a line of symmetry for this quadrilateral. So I'm going to draw that line here. This is my line of symmetry. And what that tells me is that if I reflect this side, so angle ABC, over this line of symmetry, it's going to map perfectly onto that side. Now let's read our questions. Based on the line of symmetry, explain why the diagonals AC and BD are perpendicular. So we have AC, which is our one diagonal, and our line of symmetry. And question 1 is saying, why is BD, coming right through it, going to be perpendicular? Now, if we just talked about how the line of symmetry is the same as reflecting over. So not only is this a line of symmetry, it's also the line of reflecting. And if you go back to our reflections lessons, you remember that to determine a reflection, what we do is we'll draw a line perpendicular to the line of reflection, and the same distance on the other side will be our reflection point. So because the line of symmetry gives us the line of reflection, and B reflects onto D, therefore this diagonal, or this segment that connects B and D, always has to be perpendicular to our line of reflection, or in this case, we're also calling it the line of symmetry, or the diagonal AC. 3 names for the same thing. Question 2. Based on the line of symmetry, explain why angles ABC and ADC have the same measure. So angle ABC is right here, and angle ADC is right here. So we're going to draw that double lines. Well, we just talked about how our line of symmetry is the same as a line of reflection. And what we know about rigid motion or transformations or isometries or rigid transformations is that they preserve angle measure. So when I reflect this angle all the way down to this angle, the measure stays the same. And that is true for every single reflection that is out there. It preserves the measure of angles. So when an angle is reflected, as this one is, and we know that because it's the line of symmetry, we know that the angle measures are going to be the same. Let's go on to question number 3. Problem 3. And make sure to pause in this video if you need to go over what I'm saying, because I am verbalizing the answers, but I'm not writing them down. So if you need to take a second to write it down, feel free to pause at any time. Problem 3. 3 line segments form the letter Z. Rotate the letter Z counterclockwise around the midpoint of segment BC. So if you remember from my last video, when we have rotations, we're always looking for 3 things: the direction, the center of rotation, or the point of rotation, and the degrees. So we have all 3 things here. And we're rotating counterclockwise, which means we're going this direction because our clock looks like this. That direction is the way our clock goes. That's clockwise. The opposite direction is counterclockwise. We're going to rotate it counterclockwise around the midpoint of segment BC, 180 degrees. Describe the results. Well, he's going to go all the way around. And I would recommend you take a piece of tracing paper out, you put it on top of your Z, and you do this rotation yourself. But I'm pretty sure angle B is going to go to angle C, A is going to zoom all the way down to D, and C is going to go back to B and A. So when we actually rotate him, he's going to end up in exactly the same position. And this guy has a special name. This is called rotational symmetry. And I believe we're going to be talking about this more. So the result is that the figure looks exactly the same, just rotated 180 degrees. Problem 4. There is a square, ABCS, inscribed in a circle with center D. So we have a circle. We have a square who's inscribed. The square is labeled ABCS. The center is D. What is the smallest angle we can rotate around D so the image of A is B? Well, there's an easy way to figure that out. When we have a regular polygon, and that is going to be a polygon that has all 4 sides, or all of the sides are the same length, and all of the angles are the same length, we're going to say 360 divided by the number of sides of the polygon is 90 degrees. So if we rotate him 90 degrees, and it has to be clockwise, and specifically in this figure, it depends on where you put your A's and B's, A goes to B, and is that image. So the answer would be 90 degrees, and we're done. And this is the minimum angle of rotation. If we did a second 90 degrees, A would go to C. If we did a third 90 degrees, A would go, or 270 degrees, A would go to S. And a fourth 90 degrees, which would be 360, would bring A all the way back to A. And that is our rotational symmetry for this shape. Problem number 5. Points A, B, C, D are vertices of a square. Okay. So we have A, B, C, and D. Point E is inside of the square. Explain how to tell whether point E is closer to A, B, C, or D. Well, if I'm looking at C and D, I know if I draw a perpendicular bisector between C and D, then E, if it's on the left side of the perpendicular bisector, it's closer to C. And if it's on the right side, it's closer to D. Now I can do this by drawing a perpendicular bisector for both sides of the figure. And then I'm going to draw a perpendicular bisector in this way as well. And what this does is it splits the square into 4 quadrants. The quadrant which E is in is the vertex that it is closer to. If it is on any of the lines itself, then it is equidistant to the vertexes that the perpendicular bisector is bisecting that line of. If it's in the direct center, it's going to be equidistant to all 4 points. But the easiest way here would be split it into 4 quadrants and identify which quadrant point E is in, and it will tell you which vertex it is closer to. Now in my example, E happens to be closer to A, but it doesn't specify where E is. So you're describing the process, not necessarily the actual vertex that E is closest to. All right, problem number 6. And we got to zoom out for this question. We have lines L and M are perpendicular. So we have M is perpendicular to L. We're just going to go ahead and we're going to have to write out the letters for this answer. We have M is right here. L is right there. They're perpendicular, so we mark it with a box. Sometimes reflecting a point over M has the same effect as rotating the point 180 degrees using center P. Select all labeled points which have the same image for both transformations. So let's see. B reflected over M is going to be B prime, and he's going to be right there. D reflected over M is going to go right about over there. That's D prime. E reflected over M, I think he's going to land up right about where A is. So we're going to say E prime. A reflected will go about where E is. And then C reflected is going to come over right about over here and be C prime. Now let's rotate each of these degrees, 180 degrees, and see what happens. B rotated 180 degrees around center P. He's going to come all the way down here, and our rotation points are going to be in pink, is B prime, so they don't line up. So not B, cross it out. A rotated 180 degrees. Well, he's going to come over here. He's going to be A prime. Okay, our pink A prime and our blue A prime line up, so A is going to be one of our answers. E rotated 180 degrees around point P. He's also going to be E prime, so E is one of our answers. C rotated 180 degrees around point P. Well, I'm going to draw a line straight through because C has to go 180. C prime is going to end up over there. Our pink and our blue C prime don't match up, so it does not work. D rotated 180 degrees. D is going to go 180 degrees. He looks like he's going to almost land on our C prime, but our pink D prime and our blue D prime do not match up. And those are all of our points. So the correct answers are A and E. Now be careful with the multiple choice below. I'm going to let you fill that out yourself because these are the points. Make sure that you're identifying the answers A and E rather than the actual letters A and E. So the correct answers would be A and E. They match up the letters, which is smart. All right, problem number 7. Here's triangle POG. So we got triangle POG. Match the description of the rotation with the image of POG under that rotation. All right, so we're going to do 2 and 3, and then we'll have to go down for 3 and 4. So POG, what happened here? I'm pretty sure, he was rotated. And we could either say he was rotated so OP went up to O prime P prime, right? Because he kind of got rotated like that. Nope, he got rotated like this. Now that looks like it's a 60-degree rotation because this angle is kind of rotating 60 degrees, and that is counterclockwise, which actually happens to be the same thing as, well, this is not any of our answers, so we're going to save that for a future lesson. But it is the same thing as 270 clockwise, but we have 60 degrees counterclockwise around point O, so check. We figured out the first one. Let's go on to the second one. What's happening here? Well, here it looks like angle OPG kind of rotated, so it's in this direction. And I'm kind of just taking this triangle and I'm putting it up here, which means this angle rotated, let's say this way. And he rotated, well, let's look at a line because it's hard to figure out just by an angle. So OP rotated 60, 120 degrees counterclockwise. I look at this and this is not one of our answers. So we are going to, actually no, I apologize. It is not one of our answers. So we have to figure out where did I make a mistake. And the mistake I made is that this direction is clockwise. So we rotated OP went 120 degrees to line up with OG because that's where our new O prime B prime is, and it's 120 degrees clockwise around point O. And we are all susceptible to mistakes. I have taught geometry for 7 years, and I occasionally make mistakes. We just got to make sure that we're double checking our answers so that the mistakes don't cause problems. So we have 2 more options left. So let's zoom out a little bit. We can do some mix and match here. We identified the first one. That was a 60-degree counterclockwise rotation around O. We identified the second one as 120 degrees clockwise around O. And the third one Well, it looks like we're rotating around point P because it looks like the triangle came up kind of over there. And so our center of rotation is P. The only option around point P would be 160 degrees clockwise, and that makes sense because remember our clock goes all the way around. So when he went here up to there, we rotated clockwise 60 degrees, which gives us our last answers as 60 degrees clockwise around O. And that makes sense because if we're looking at this triangle, we have, if we're rotating around point O, 60 degrees clockwise is going to take this point, bring him here. This point's going to come down here, and we're going to end up over there, which looks like our figure. Now, rotations is the type of thing that the more you do, the more used to you get to seeing what a rotation is. So if you're having trouble with rotations, I just recommend doing a lot of them and getting used to looking at the pattern. Don't just do them to do them. Think about the pattern, think about what you're seeing, and you'll get better at them, I promise. If you have any questions, go ahead and put them in the comments. If you like this video, please make sure to like and subscribe. And if you want personalized videos, you can sign up for my Patreon and I will make you whatever you need. I'll see you in the next one.